Hello and welcome to another session in physics. In this session we'll be looking at the topic alternating currents part 2. But before that, let us review the previous lesson. Welcome back. At this point, let's talk about reactance and impedance. According to the slide here, you'll see that reactance is defined as opposition offered to the passage of an AC by either an inductor or capacitor or both of them. Reactance that comes as a result of an inductor is called inductive reactance. On the other hand, reactance that comes due to a capacitor is called capacitive reactance. On the other hand, impedance is the overall opposition that is offered to the passage of an AC mixed circuit containing a resistor and any one or both of an inductor and a capacitor. So when you get a resistor, an inductor and a capacitor, it forms an RLC circuit. Resistor, inductor represented by L and capacitor by C, and this gives birth to impedance. Impedance, yes. So both reactance and impedance are measured in ohms. Also, reactance is found by the ratio of the amplitude of voltage across inductor or capacitor to the amplitude of current across inductor or capacitor. Remember that Ohm's law said that V is equal to IR. So when we make R the subject of the equation, we divide both sides by I. Therefore, resistance is equal to V over I. So a reactance here is more like a resistance. So therefore, it's only reasonable that it is the amplitude of the voltage across the capacitor or the inductor over the amplitude of the current across inductor or capacitor. This is a simple AC circuit showing a resistor, an inductor, a capacitor, and the voltage that has been applied across it. This is a full diagrammatical representation of how a resistor circuit looks like. This is a capacitor circuit. This is a resistor plus capacitor circuit. This is an inductor only circuit. This is a resistor plus inductor circuit. And this is impedance, resistor, inductor, and capacitor circuit, where this sign shows the AC voltage from the AC generator or wall socket. And this shows the resistance or the incandescent light filament represented with R. And this is the symbol for switch represented by S. And this is the symbol for inductor represented by L. Capacitor represented by C. I'd like to point out that the SI unit for capacitor is farad. For inductor, it's Henry. For the resistor, it is ohms. So let's get these points at the back of our mind. The symbol for ohms. Now let's start with talking about an AC circuit containing only a resistor. AC circuit containing only a resistor. An AC circuit containing resistor is given from Ohm's law, which stems from R equal to V over I, and we have the instantaneous voltage, which is V over I, like we've written here before, RMS, and here we have our RMS as well, and this is our peak value of voltage and peak value of current, sine angular phase over sine angular phase, and it is given by peak value of this and peak value of this too, where sine angular phase will cancel out sine angular phase. Let's take a question. Here from this question, we have that a voltage supply of 12 volts of RMS and frequency 90 Hertz is connected to a 4 ohm resistor. It's connected to a 4 ohm resistor. We're asked to calculate the peak value calculate peak value of the current. Now, the solution to this question is going to be our RMS voltage, which is 12 volts, our resistance R, which is 4 ohms. Now, from R equal to RMS volts over RMS current, we're going to have our RMS current equal to our RMS voltage over the resistor itself, which gives us 12 over 4. 4 divided 12, this is 3 amperes. That is the answer to this question. At this point, let's look at an AC circuit containing only a conductor. AC circuit containing only a conductor. Now, from Ohm's law as well, where V is equal to IR, we know that the voltage across the inductor, which is represented by L, is given by I times XL, like current times inductive reactance. Inductive reactance which is XL, is given by peak value of voltage over peak value of current, and is also given by RMS volts over RMS current. It's also given by the angular velocity times the inductor equal to 2 pi FL. So this is the formula we use to find inductive reactance. So the inductance of an inductor L can be given by voltage across inductor over 2 pi FL, or inductor equal to voltage across inductor over the angular inductance. Now let's take a question here. Let's take a question. The question goes this way. Let's say we have a simple circuit drawn like this, and then we have the inductor connected here, and the value of this inductor is equal to 0.9 Henry. The value of this inductor is 0.9 Henry, and we are told that the frequency of this circuit F is equal to 500 over pi hertz. 500 over pi hertz, and they're asked to find the reactance of the inductor. We're asked to find the reactance of the inductor, which is inductive reactance. So inductive reactance X with subscripted L is given by 2 pi FL. 2 pi FL. So we continue. XL equal to 2 pi times the 500, which is over pi, which is our frequency. We'll multiply it by 0.9, which is the value of the inductance here. So our answer is going to give us something like this: 2 times 500 times 0.90, which is equal to 900 ohms. And that is the answer to this question. At this point, let's look at an AC circuit containing only a capacitor. Also, from Ohm's law, we know that V is equal to IR. I want you to notice how everything is hinged or based on Ohm's law. So the voltage across the capacitor, which is VC, is equal to current times capacitive reactance. Capacitive reactance XC. But if it is XL, it is inductive reactance. So capacitive reactance XC is given by the RMS voltage over the RMS current, equal to 1 over, this is 1 over the angular capacitance, which is also equal to 1 over 2 pi FC. Now from VC, voltage across capacitor equal to the current times capacitive reactance, and the capacitive reactance equal to 1 over 2 pi FC. The capacitance of a capacitor C can now be given as 1 over 2 pi FVC, where VC is the voltage across the capacitor, or capacitance equal to 1 over the angular velocity times the voltage across the capacitor. Now let's see that we have a question like this. The question says, at what frequency would a capacitor of 2.5 microfarads used in a radio circuit have a reactance of 250 ohms? This is the question. Now the solution to the question is that we have our capacitive reactance, which is equal to 1 over 2 pi fc. But before that, let's see what and what we have to help us find the answer to this question. First of all, let's try to find our capacitors. Our capacitors here, the capacitance is given as C equal to 2.5 microfarad. And when we're talking about C equal to 2.5 microfarad, we simply mean 2.5 times 10 raised to the power minus 6 farads, because micro means times 10 raised to the power minus 6. And then already they told us that the capacitive reactance is 250 ohms. So we're asked to find the value of the frequency. So therefore, from this equation, our frequency, making f the subject of the equation, is going to become 1 over 2 pi capacitance times the capacitive reactance. So we continue to solve. F equal to 1 over 2 pi times 2.5 times 10 raised to the power minus 6 times the capacitive reactance, which is 250. It gives us 1 over pi times 1250 times 10 raised to the power minus 6, which gives us 1 times 10 raised to the power 6, because the law of indices states that when this subtraction sign to the power, the negative index, when it goes up, it becomes positive. So we have pi left underneath, and we multiply it by 1250. This now gives us f as equal to 1 million. 10 raised to the power 6 is 1 million. 1 million over pi times 1250, and when you divide everything, it's going to give you 800. You divide 1 million by 250, you will get 800 over pi hertz. So this is our frequency, f equal to 800 over pi hertz. Thank you so very much for joining us in this lesson. To refresh your memory on what we've just discussed, please take the test that will appear on your screen.